Capacitors with dielectrics. In this module, we will outline the key topics covered regarding dielectrics. We will start with a clear definition and the fundamental properties of dielectrics. Then, we will explore the specific effect of dielectrics on both capacitance and voltage within a given circuit. We will also look at the atomic view, specifically focusing on the physical meaning of the dielectric constant kappa. Following that, we will discuss the concept of dielectric strength and how it ultimately determines the maximum operating voltage of a practical capacitor. Finally, we will determine how to calculate the energy stored in capacitors when dielectrics are present in the system. Let us begin with a basic introduction to dielectrics. A dielectric is essentially a non-conducting material, such as rubber, glass, or waxed paper, which when one of these insulating materials is placed between the plates of a capacitor, it fundamentally modifies the electrical properties of the device. Capacitors serve as critical energy reservoirs in a variety of high-power devices, including portable defibrillators, camera flashes, and fusion lasers. As a fascinating real-world example, the atmosphere of the Earth can be modeled as a huge capacitor, with the ground and the upper air layers acting as the conducting plates. Next, we will look at an experimental observation involving dielectrics. Consider a charged capacitor with an initial charge Q0 and an initial potential difference delta V0, starting with only air between its parallel plates. If a dielectric material is then inserted between these plates, a connected voltmeter will show a measurable decrease in the voltage to a new value, simply called delta V. The relationship between this new voltage and the initial voltage is defined by the dielectric constant, which is represented by the Greek letter kappa. Specifically, the new voltage delta V equals the initial voltage delta V0 divided by kappa. Since the new voltage delta V is less than delta V0, it logically follows that the dielectric constant kappa must be a value greater than 1. Now let us closely examine the overall impact on capacitance. Because the charge Q0 remains completely constant when the charging battery is removed, the overall capacitance C must logically change. The new capacitance C equals the charge Q0 divided by the new voltage delta V, which mathematically is equivalent to kappa times the initial charge Q0 divided by the initial voltage delta V0. This sequence results in the fundamental relation that the new capacitance C equals kappa times the initial capacitance C0. For a standard parallel plate capacitor, this means the new capacitance equals kappa times the constant epsilon 0 times the plate area A, all divided by the separation distance d. This slide helps us in visually understanding the dielectric insertion process. The physical insertion of a dielectric always increases the capacitance by a factor of kappa. You should carefully note that if the battery had remained connected during the insertion, the voltage would stay constant while the charge on the plates would increase, such that the new charge Q equals kappa times the initial charge Q0. However, in our visualized example, the potential difference across the charged capacitor is initially delta V0. After the dielectric is smoothly inserted between the plates, the charge Q0 remains exactly the same, but the potential difference visibly decreases while the overall capacitance of the system increases. We must also carefully consider the concepts of dielectric strength and breakdown. Dielectric strength is defined as the absolute maximum electric field a material can withstand without becoming electrically conductive. If the applied electric field exceeds this critical limit, the insulating properties of the material completely break down, which leads to a dangerous electrical discharge. Because of this, the working voltage is defined as the maximum rated voltage for a specific capacitor to operate safely and avoid this breakdown scenario. Different insulating materials have vastly varying properties. For example, Pyrex glass has a dielectric constant of 5.6, while Teflon has a dielectric constant of 2.1, and each possesses their own specific dielectric strength. Using a dielectric provides three main functional advantages in modern capacitor design. First, it leads to a direct increase in capacitance, effectively multiplying the original capacitance C by the factor kappa. Second, it allows for a significant increase in the maximum operating voltage, which is directly due to the high dielectric strength of these solid materials when compared to plain air. Third, it provides crucial mechanical support between the components. This solid structural material allows the conducting plates to be placed very close together, meaning the separation distance d can be extremely small, without any risk of the plates physically touching each other. Let us look closely at an example calculation regarding the energy stored in a capacitor. Suppose a capacitor is fully charged to an initial charge Q0, and then the charging battery is completely removed. A dielectric slab is subsequently inserted into the device. We need to mathematically find the change in stored energy. The initial energy, U0, equals the square of the charge Q0 divided by 2 times the initial capacitance C0. The final energy, U sub E, equals the square of the charge Q0 divided by 2 times the new capacitance C, which further simplifies to the square of Q0 divided by 2 times kappa times C0. Thus, the final energy, U sub E, equals the initial energy, U0, divided by kappa. Since kappa is always greater than 1, the stored energy actually decreases. This seemingly lost energy corresponds to the macroscopic mechanical work done by the capacitor as it physically pulls the dielectric slab inward. To successfully prevent errors in your physics calculations, always remember these pitfall prevention rules. First, if the capacitor remains physically connected to a battery, the potential difference delta, V, is forced to remain constant, while the stored charge Q changes. Second, if the capacitor is disconnected from the battery entirely, it acts as an isolated system for electric charge. In this disconnected case, the total charge Q remains perfectly constant, while the potential difference delta, V, changes dynamically. You must always correctly identify the status of the battery connection before attempting to calculate any circuit modifications. A highly practical application of these theoretical principles is the common stud finder used by carpenters around the world. A stud finder utilizes a capacitor with side-by-side plates rather than the traditional facing plates. When the device is physically moved over a wall, the material located near the plates changes. Initially, the materials existing between the plates are simply the wallboard and air. When the device moves across a hidden wooden stud, the materials become the wallboard and the solid wood stud. Since wood has a significantly higher dielectric constant than air, the overall capacitance of the sensing device increases. This sudden change in the dielectric constant triggers an internal circuit that causes a signal light to illuminate, indicating the exact location of the stud. In summary, dielectrics are versatile insulating materials that inherently increase the capacitance of a device by a multiplicative factor called kappa. For an isolated capacitor, physically inserting a dielectric proportionally reduces the voltage, such that the new voltage delta, V, equals the initial voltage delta, V0, divided by kappa. Furthermore, the specific dielectric strength of the chosen material naturally limits the maximum electric field it can handle, which in turn sets the maximum safe operating voltage. Finally, the total energy stored in an isolated capacitor decreases upon the insertion of a dielectric, primarily because the electric field does positive mechanical work on the slab to pull it inward. Before we conclude this topic, please consider these review questions to thoroughly test your understanding. First, if a simple capacitor is charged and then cleanly disconnected from a battery, what exactly happens to the energy stored in the electric field when a dielectric is inserted, and where does that physical energy go? Second, Why does using a solid dielectric material allow for a much smaller physical separation distance d between the plates of a practical capacitor compared to using standard air? Please take a brief moment to reflect on these critical questions based on the fundamental concepts we have covered.